Okay, so I think the screen's now recording. We'll give it a shot. Can I write on the screen again? No. All right, folks, let me close the program and reopen it.
Sorry.
No, it's okay. I'm not sure what's going on.
Now we all have to stay.
Oh, there they all are.
Wiggles.
All right, we seem to be back in business. All right. So we've got, for this problem here, we're going to go ahead and let's find the eigenvalues and eigenvectors and eigenspaces of this. So we're kind of getting familiar with this. To find the eigenvectors or the eigenvalues, we're going to solve this equation: 1 minus lambda, 1, 1, 1 minus lambda. And when we go ahead and compute that by our means of computing the determinant, we've got lambda squared minus 2 lambda plus 1 minus 1 times 1. Let me write it like that. And so that gives us lambda squared minus 2 lambda, and we want lambda squared minus 2 lambda, that determinant, to equal 0. So we get lambda times lambda minus 2 needs to equal 0. So we get lambda equals 0 or lambda equals 2. And I just felt it was important for you to see an example where you have 0 as an eigenvalue, but really nothing changes. Okay. When we go to find the corresponding eigenvectors, let's pick lambda equals 0. We're going to return to this equation here. The equation a minus lambda I times the vector v, the vector equation, needs to equal the 0 vector. And so what do we end up with? We end up with 1 minus 0, excuse me, 1 minus, let's see, lambda, so 1 minus 0 1 minus 0 times v1, v2 needs to equal the 0 matrix, or the 0 vector. And so we're just going to go ahead and solve this system of equations here. 1, 1 augmented with 0, 1, 1 augmented with 0. When we row reduce this, we get 1, 1, 0, 0, 0, 0. And so we find that v2 is free and that v1 is equal to negative v2. So our eigenvector then, or an eigenvector associated with 0, let's pick v2 as 1. And so we would find negative 1 for v1. And so we found a corresponding eigenvector associated with that. I heard some grumblings or concerns. Any questions?
That's my dog, actually.
Oh, okay, no worries. Okay. All right, so then what's our eigenspace? The eigenspace of lambda equals 0 then is simply the span of this vector negative 1, 1. Okay. So I'm going to stop with this problem. We would then go ahead and repeat this for lambda equals 2, but there's no new material there to show. Are there any questions on this example, folks?
So geometrically, what this means is everything along that line gets smushed into the 0 vector after the transformation, right? That's why it has a 0 determinant as well.
Yes. So because 0 is the eigen, and that's related to it having a 0 determinant, yes. So any vector gets along this span is equal to just lambda times that vector, but lambda here is 0, and so everything gets smushed down to the origin. Yes, that's correct. And so because of that, because some of the vectors are getting smushed down to the origin, you're necessarily going to lose at least one dimension under your transformation. And so that's why we have a 0 as a determinant. That's one way you could see we have 0 as a determinant. Yes. Yeah. Okay. So folks, let's go ahead now and look at letter C here. So I'm going to go ahead and move this F to the side. Oh. So let's look at letter C here. And let's see where we have some repeated eigenvalues, and let's see what happens. Now, I'm not going to go ahead and find completely find the determinant of this. I'll go ahead and set it up. So we're going to solve for the determinant of, let me put it over here. So for letter C, let's see here, let's do this. So for letter C, we're going to set -2 minus lambda 1, 1, 1, -2 minus lambda 1, 1, 1, -2 minus lambda. We're going to set that determinant to be 0. Okay? So we have to compute that determinant. I'm not going to compute the whole thing because it's a little bit tedious. So I'll get it started and then I'll just jump to what the characteristic equation is. So you would go ahead and, let's say, choose to expand along this row. And so you'd have -2 minus lambda times the determinant of -2 minus lambda, 1, 1, -2 minus lambda. That's for the first minor. Minus, for this one right here, remember that gets a minus sign, -1 times, and then we'd have 1, 1, 1, -2 minus lambda. And then for this third entry, we'd have +1, and we'd have 1, 1, -2 minus lambda 1. Okay. Any questions about how you would continue to find the characteristic polynomial for this? It'd be a mess, but it would just take a little bit more time than we have. So I'm just going to go ahead and jump to it. And this characteristic polynomial comes out to be lambda times, in fact, if you did it, you get lambda cubed minus 6 lambda squared minus 9 lambda. And then if I set this equal to 0 and solve for lambda, that would happen when lambda, let's pull out the minus lambda times lambda squared plus 6 lambda plus 9 equals 0, or when lambda equals 0, or lambda equals -3, and this has multiplicity 2. Okay. Folks, so I didn't show the work to go from here to here. In the problem that I ask you to do, where is it? Where's your problem? In the problem I ask you to do, notice that, well, your coming up with your determinant will be a lot easier because you can expand upon this column, and then you can go ahead and expand upon this column, and it'll be a lot easier to compute because of all the zeros in that. Okay. So are there any questions about how we found these eigenvalues for this matrix? Nope. Okay. So the question is what happens when we have repeated eigenvalues? Okay. What happens when we have these repeated eigenvalues? Well, let's go ahead and pick that one for when lambda equals -3. We're going to look at this equation here. We're going to look at a minus lambda I times our vector v needs to equal the 0 vector. And so we'd have -2 minus 3, -2 plus 3, 1, 1, 1, -2 plus 3, 1, 1, 1, -2 plus 3. Let me just double check that. Yes. For this determinant, or sorry, not this determinant, for this matrix, times our v1, v2, v3 needs to equal the 0 vector in 3 space, which is 0, 0, 0. Any questions about that, folks?
Nope.
Why don't you just say everyone say okay if you're doing okay. Just I haven't heard any response from you for a while, so I'm getting.
I'm doing great.
Doing great.
I'm good.
That's perfect.
Okay.
All right. Okay, so then this cleans up to be just the system of equations 1, 1, 1, V1, 1, 1, 1, V, oh, sorry, not V1, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0. When I row reduce this, notice in this case, I'm going to get 1, 1, 1, 0. Then this will be a row of all zeros, and this will be a row of all zeros. What does this mean, folks? This means that V2, since it's not a pivot row, is free. And V3, since it's not a pivot row, is free. And then V1 is equal to negative V2 minus V3. Are there any questions about that?
No, I'm good.
Did I hear a question from someone?
No, we're good.
We're good. Okay. So we can pick any numbers we want for V1 and V2. Let's go ahead and pick 1 and 1 for each of those. And that would make V1 then negative 2. So let's see here. I'm sorry. That's not what I want to do. That's a fib. What I want to do is I want to write this the way I had you practice writing these way back when we were doing these systems of equations. And so we could rewrite this solution as whatever our choice is for V2. So let's call it R times negative 1, 0, and 1, negative 1, 1, and 0. Well, first, let me put this in the complete form, and then you can see what I mean. So our solution vector to this, we could write as 0, 0, 0 plus R times negative 1, 1, 0 plus S times negative 1, 0, 1. Are there any questions how I just represented that vector?
Yeah.
Okay. So remember when let's see if I can come up with an example quickly. If we were solving a system of equations and we got, how do I do this quickly?
I don't know if this helps, but Ed, for like choosing V2, just choose R, and for V3, just choose S. So then if you were to use a single matrix, it would be the V1 is going to be minus R minus S, V2 is going to be R, and V3 is going to be S, and then you just spread it out.
Yeah.
Oh, okay. I see.
Okay. So yeah. So but the point is now we can write each one of these in terms of a vector with an arbitrary parameter in this. And so in this case, we're going to write our eigenvector. We're going to have two eigenvectors here. And so one eigenvector is, let's pick 1 for R. And so we'd have that the first eigenvector is minus 1, 1, and 0. And then we're going to pick 1 for S. And so our second eigenvector is minus 1, 0, and 1. Okay. So the eigenvectors for lambda equals, I think it was negative 3, are negative 1, 1, 0, and negative 1, 0, 1. Or put another way, the eigenspace for lambda equals negative 3, the eigenspace for lambda equals negative 3 is the span of these two vectors. So in this case, the span of the eigenspace is not all along a line passing through the origin, but this particular plane passing through the origin in 3 space.
So did we know that was coming because we had multiplicity 2 for lambda equals -3?
We didn't know that was going to happen, but we knew it was a possibility. So if the multiplicity of the eigenvalue is 2, we knew that the span could have a basis, or let me put it like this, the eigenspace could have a dimension up to 2.
Would you consider this a unique solution?
Unique solution. Well, any other multiple of this vector. So for example, -2, 2, and 0, and 5, 0, -5. These two vectors, one is, notice I just multiplied the first one by 2, and I multiplied the second one by -5. This would also be a span for your eigenspace. Or you could also group these two and say those are two eigenvectors for the associated eigenvalue -3.
Okay.
Yeah. So let's go ahead and look at this one more example. And we may not get through all these. So let me move all this off to the side here. Folks, I appreciate your patience as I deal with not all
Technology.
technology's fault. It's partially mine as I get going through this. My hands get sweaty and I can't use this machine as well. Okay. So now let's look at letter D here, where we've got repeated eigenvalues with the same. We're going to see that they have the same eigenvector. So to Isaac's question, he said, "Hey, we have repeated eigenvalues. The -3 was repeated twice. Is that how we knew it was going to have a basis of 2?" And I said, no, it could have up to a basis of 2. And we're going to see that happens here. So let's go ahead and find the eigenvalues of this matrix. Let me think for just a second. Yeah, because you'd expand along that. And then, yeah. So when you have a diagonal matrix like this one, notice that we can compute its determinants much more easily. So when we go to find A minus lambda I, determinant needs to equal 0. That's going to be 1 minus lambda, 1, 1, 0, 1 minus lambda, 1, and 0, and then 1 minus lambda. When you go to compute that determinant, because it's a diagonal matrix, the determinant is simply going to be 1 minus lambda cubed. Okay. Does everyone see why? Should we do it?
Yes.
Yeah, let's do it. So I'm going to go ahead and, since it's diagonal, it makes sense to expand this way. So you'd have 1 minus lambda times the determinant of 1 minus lambda, 1, 0, 1 minus lambda. But then I'd have, in continuing to expand by minors, we'd have minus 0 times the next determinant, and then plus 0 times the next determinant as I go down that way. Does that make sense?
Yes.
But notice in this case, the only thing that matters in this 2 by 2 matrix is the multiplication of A and D. And so we get 1 minus lambda times 1 minus lambda times 1 minus lambda. So in this case, we get lambda equals 1 with multiplicity 3. Okay. So when we go to find eigenvectors, we could have 1 free variable, 2 free variables, or 3 free variables, depending on how this works out. So Isaac, that sort of answers your question there.
Yep.
And I think in this case, we will find that we'll still just have one free variable. So when we return to our matrix equation, A minus lambda I times V needs to equal the 0 vector. We would have, let's go ahead and pick, so we've only got one choice, it's 1. So we'll have 0, 1, 1, 0, 0, 1, 0, 0, 1 times our unknown V1, V2, and V3. That
Isn't it
needs,
0, 0, 0, 0 on the bottom?
what's that?
Isn't it 0, 0, 0 on the bottom?
0, 0, 0, yes, that's correct. Thank you, Edward. Yep. So when we put this into row reduce, it will have 0, 1, 1, 0, 0, 1, 0, 0, 0, augmenting it that with 0, 0, 0. So what do we find here? In this case, we see that V2 has to equal 0. V3 is free. And two has to equal 0. This says V2 plus V3 has to equal 0. So V2 equals minus V3. Just a second here, folks.
Is that V3 equals 0 for the second line?
For V1 equals 0.
V2 equals 0.
Give me just a second here.
Oh, yeah, V3 equals 0.
Oh, sorry. So this tells it. So I'm sorry. This doesn't tell us V3 is free. This equation right here tells us V2 equals 0. And then this tells us that V2 plus V3 has to equal 0. So that means V3 also equals 0. And then that means that V1 is, notice it doesn't have a, so V1 is free in this case.
So I interpreted free as an all, everything in the row had to be 0.
Say that again.
The way I was the way I was interpreting the problems we were doing before is that the free row was always the one that had all zeros in it.
No, remember it always had to do with pivot columns. So what I didn't do here, and I guess it would have been more clear if I had done this. Let me do this. Here's our augmented matrix, but we can finish putting it further into RREF form if we get a 0 in this position here, right? So we can do that. So that gives us 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. So what did I do? I multiplied to get this here. I said take our new row 1 is going to be negative row 2 added to row 1, and that got a 0 in that position right there. So as we read this now, this says this says V3 has to equal 0 and V2 has to equal 0. And then the choice then for V1 is free.
Okay.
Well, put another way, notice that V3 has a pivot. V2 has a pivot. So those are both determined, but V1 does not have a pivot. So that's what makes it a free variable in this case.
I think maybe a more
It's not like the actual definition, but a more useful like heuristic would be if a column is all zeros, not if a row is all zeros.
Yes, yeah, we're never saying that if a row is all zeros, then that because it's the third row, the third variable is free, right? Because I could have this matrix just fine. I could have 1, 0, 0, 3, 0, 1, 0, 4, 0, 0, 1, 5, and then I could have another more rows of all zeros, right? This doesn't mean that there's some sort of V5 or there's some sort of V4 that are free. This only has as many variables as it has columns. So when you're looking to see what's free, you're asking which variable has pivot columns and which one has columns of all zeros.
Okay.
So in this case, then, what is our we just have an eigenvector. So, and that would be picking a choice for V1. Let's pick 1. So we get 1, 0, 0 is an eigenvector for lambda equals, I've forgotten what it was now, for lambda equals 1. And so the eigenspace for lambda equals 1, since it's just one vector describes it, is just the span of that one vector. Okay. So folks, we're starting to run out of time here. What do I want to say about this? First of all, the big take-home point from today's lesson is how do we do question number 2, which is the very first thing we answered. Okay? More often than not, when we go to tackle these problems, you're going to encounter problems where you have as many eigenvalues as you have dimensions to this system. Okay? The hard part of working with eigenvalues and eigenvectors is what to do with repeated eigenvalues. And in what cases do we have, in what cases does that change our eigenspace? Normally, if you have, say, a 3x3 system and you have 3 distinct eigenvalues, then each one gets its own eigenvector that describes its entire span. The hard part is the case when you have repeated eigenvalues, because then you could have up to as many vectors as there are free you'll have as many vectors as there are free variables when you go through to solve that corresponding system. Okay. Yeah.
So just to kind of point to what you were alluding before when Isaac said, because it had multiplicity 2, we had 2 vectors, 2 eigenvectors, but you also said you could have up to. So in this case, we had lambda 1 with multiplicity 3, but we only had 1 vector.
Correct, exactly. Okay. Yeah, that's a nice summary. So in example C here, we said that lambda equaled, I think it was 3 with multiplicity 2. Is that right?
Right.
Okay. And so it could take up to 2 eigenvectors to describe the entire space of that eigenspace. Yeah. But in D, we had lambda equaled 1 with multiplicity 3, and we only had 1 eigenvector still. We could have had 1, we could have had 2, or we could have had 3 linearly independent eigenvectors. And whatever those eigenvectors are, those become the span of the corresponding eigenspace. Okay. So folks, I'm running out of time here. Let me just, we'll pick up more of this I'm not going to try to force us to be on a schedule. So I'm going to work through this document more next time. I think that I would like to go ahead, and so everyone's here. Let me just say that you should have 6, 7, 8, and I I'd like you to try 6, 7, 8, and 9. Let's do this. Go ahead and submit 6, 7, and 9 before the next class. Okay. Number 8, I'll let you guys work on in class next time. And as well as, and then number 10, I'll let you do number 10 on your own next time. Okay. So if we could work these and submit them before the next class, 6, 7, and 8. And I think you guys have already worked through number 6. So you've just got 7 and 8 to do. Does that sound fair?
Yeah.
Sounds good to me.
Yep. For the
Okay.
homeworks, I think I saw 2 of them. Are they due like tomorrow and the next day, the following day?
Let me check on that here. Let me pull up our WebAssign. Sure if we got a. No, I can't do this.
What is today, the 7th? Yeah,
It
tomorrow
is.
and the next day.
So I've got them due on the 9th. I think I'll go ahead and give you guys some more time on that. So let's have those two WebAssigns. Let's have those 2 WebAssigns due just by Sunday.
I mean, I'll only procrastinate.
Yeah, well, that's why I want you to make sure you hand these in by next time.
So did you say 6, 7, and 8 or 6, 7, and 9?
6,
That looks
7,
like
and
6,
9.
7, and 9. Okay.
And you have all the tools to do 8 as well, but you might look at that and think it seems a little daunting. I would go ahead and try it because you're going to have to do it anyway, but I'll give you guys some chances to work on that in class on Thursday. Okay.
Okay.
Real quick, folks, before I let you go, I want to give you a motivation for where we're going. So we didn't get to this today, and I'm not going to try to rush it, but I just want to show you pretty soon we're going to look at solving a system of linear differential equations. And it turns out that the eigenvalues and eigenvectors of the corresponding matrix are going to be exactly what we need in order to talk about the solution to that system. So there's just a real brief motivation for where we're going.
Okay.
So by being able to find eigenvalues and eigenvectors of a matrix, we're basically done with solving systems of n-linear ODEs. So for example, if lambda 1 and lambda 2 are eigenvalues, with v1 and v2, they're eigenvectors. We will see next time that the solution to this is just this pair of equations that looks like e to the lambda 1t times v1 plus e to the lambda 2t times v2, and that's how we solve systems of linear ODEs. Okay? The hard part will be, of course, dealing with the cases where you have repeated eigenvalues, or where you have complex eigenvalues. So those are going to be the 2 hard cases that we'll have to deal with, and we've got a couple days yet to deal with those slowly. Okay?
Are those also going to look a lot like what we've already been doing, where like you just stick another factor of t in there?
Great
If you've
question.
got repeated.
That's a great question, and that would be a good first guess, but it turns out that that's not quite going to be good enough for when we have the repeated eigen values. We will stick in a factor of t, but we need to then find something that's sometimes called like another false eigenvector to go with it. So we'll talk about how to do that. Okay. So folks, the big takeaway from today, as I said though, the big takeaway from today, as I said, is to, this is the wrong one, is to, can you find eigenvalues and eigenvectors of a matrix? And we see that, yeah, it gets a little bit harder if the eigenvalues are negative, and it gets a little bit harder if the eigenvalues are repeated. Okay? But the vast majority of the ones that you'll see in those WebAssign works are just distinct eigenvalues and distinct eigenvectors. And so it's a pretty straightforward process. Okay? We'll pick this up next time, but if you would submit these 3, that's all I've got for you for homework until the next class, is to submit these 3 into D2L. and then we'll go ahead and pick up with this next time. Okay. That's all I've got for you. I can stick around though as long as you have questions. Otherwise, you're welcome to take off.
I have a question.
Yeah, Isaac.
So,
Oh, or is it whoever? Sorry, I've got a
Yeah, it was good. It was good.
yes, to submit the 6, 7, and 9, there's a specific drop folders for each one, right?
That's correct. Yes. So if you go into, if you go to our class D2L page, go to our class D2L page and you look under content, under week 11. Let's see if I'm in student view or not. Let me put myself in student view. Go under content, look at week 11. Then you can see there was your pre-work. And then for in-class Eigenstuff, we've got one for 6, one for 7, and one for 9.
Okay, and the pre-work, is that was that graded, or can we still turn it in?
Yes, so if you didn't get it in, go ahead and get it in. I'll still take it. But yeah, so sometimes I'll have pre-works for these, and I want you to try your best to get them done beforehand. Do look at that because they have me working through these problems in videos, and I think that that's particularly helpful. Yeah.
Okay, great. Thank you.
Yep. Folks, other questions?
I
I
have
have one that's not related to the work, but if somebody else first.
mine's a test question. I don't know what yours is. You can go if it's not gonna. I don't know.
No, you go first because yours is actually about class stuff.
Okay, I actually just have a real quick question on, I believe it was the proof of number 10. I missed some points there, and I guess I don't know what I missed. So I feel like just conceptually would be, I need to clear that up.
Yeah.
And that was rough.
Sure. Give me 1 second.
No
Let's
worries.
put that on the back burner real quick, Isaac. First of all, were you able to see where I uploaded the solution for you to look at?
Ooh, I don't know.
Generally, unless what you missed was very easy for me to make a correction on, I usually uploaded a solution with it. So
Wait,
if you
I
go
think-
back and look at that missed question, you may be able to find a photo of the solution.
Okay, cool. I'm gonna go check that out.
Yeah,
That's
and
cool.
if you want to hang on, I can still pull yours up, but I'll have to stop sharing the screen, pull yours up, and then talk about it. So I might wait, see if there's other questions first.
No worries. Yeah, I'll hang around for a bit.
Other questions, folks?
Do you want us to do the ODE question on D2L as well, or just do the Eigenstuff 6,
Just do
7,
the
and 9?
Eigenstuff since we haven't talked about the ODEs yet.
Okay.
Yeah. Thanks, Chris. Gilbert.
I have a question.
Oh, Coyle? Yeah, go ahead.
So, I was trying to look for the link you sent to get into WebAssign, but I couldn't quite find it. I don't know if I actually got it. Is there any chance you could send that again?
Yeah, so you've sent that email twice, and I replied to it both times.
Oh, really?
Did it not go through?
Yeah, I'm not getting the replies, unfortunately. Not sure why.
So, because I've gotten that email from you twice, and I keep responding to it. And the second time, I even highlighted the answer for you.
Oh.
So let's just see what's going on there. So remember, it's going to to charris260 at student.ccs.edu.
Okay. Would that just be
Where
on
you're emailing me from? So I'm just hitting reply.
Yeah.
Anyway,
I got it the first time. I got the first message you sent me, but then I didn't get any other ones. It's kind of weird.
okay. Maybe that's not going through. All right, here it is. So your username is simply your email address. Let me write that on here. You can still see my screen.
Yeah, I can see it.
So your username is your email address. So I put, just put Joe or J student. How did I write this? Yeah, JDoe, 23 at student.
Okay.
.cccs.edu. That's your username.
Okay.
And then your password is welcome1. That's a
All right.
capital WELCOME, then the number 1. So that W there is capitalized.
Okay. That sounds perfect.
If you need this, if you go into change any of your information, your birth year was set to the year 2000. And
Okay.
your pet name as the answer to a question was set as Spot.
Okay.
Okay. So I would recommend maybe changing that password. Although it's up to you how secure you want your account to be, whether you're afraid people are going to hack in and do your homework for you.
Oh, that would be terrible, wouldn't it?
But like when you call in to pay your bills and they want you to prove that it's you, and I'm like, do other people call in to try and pay my bills? Because you should let them.
Yeah. All right. Other questions, folks? Isaac, I haven't forgotten yours. We'll get to that.
Yeah, no worries.
Oh yeah,
I was
just
wondering
regarding. Oh, go ahead.
Go ahead.
Go ahead, Gilbert.
Yeah, and I was just telling that I was able to log into the WebAssign, but I had to go through Cengage, and then I had no problem logging in through Cengage.
Okay. Okay, that's good to know. Thank you.
No problem.
Ben, did you have any questions?
Nope, I'm good.
Okay, Nina, did you have any questions? Sorry, I've got some truck driving by. Nina, did you have any questions? Evan, do you have any questions? I can't hear any. Maybe people aren't there.
I think no one's answering.
Okay. All right. Christine, did you have a question? Was on the test?
Mine was about, was there something that you did, like when we submit photos through this Pulse app, and it's super easy and it gives us the option to like go directly to our camera and take a picture that we want to submit. I tried doing that for a different class today, and like the option wasn't there. And I was wondering if there was something in the setup that had to be done on the teacher's end.
Not that I know of.
Weird.
I think but it depends on what you were trying to upload to. Like if it was a quiz.
It was just a plain old assignment folder, like how yours are.
Yeah, I don't know.
I don't know either. I was just wondering. That was my question.
Yeah, sorry. Yeah, I don't know the answer.
No worries.
I didn't change any settings on my end that I know of. Yeah. Okay.
No worries. I keep telling my other 2 teachers to ask you how stuff works, because like my other 2 classes are unmitigated disasters right now. I'm like, you need to go ask this person what to do, because his actually work in this format, kind of.
We're trying our best here. Yeah, I don't know if I
know.
want to be providing any more.
Like, I don't got time for this.
I got an email from somebody from a community college in Oregon yesterday asking for some advice. I don't know if I want to do too much more.
Your fame is spreading.
I'm doing an amazing job myself. Trying. Okay, let me see here.
This is the smoothest running class I have right now, so.
Oh,
yeah.
Oof. Well, that's good.
By far.
We'll keep trying it. Let's see, folks. By the way, for those that are still here, I still haven't finalized tallying your test scores. All the questions have been graded, but I need to go in and actually give you a summary score. Everyone is going to get 4 points back because of the. I don't remember what question number it was.
Right.
Had the wrong
8A.
8A. So everyone's going to get 4 points back for that, regardless of whether you did it right or wrong. So yeah. Okay, Isaac, we're looking at, I think this was page 7 of the exam.
Yeah, number 10. It was number 7 of 8.
I'm still in student view. Hang on.
So if we're totaling it up ourselves, we can just add 4 to our out of 115.
Yes, you can. Mm-hmm.
Cool.
Well, not out of 115. Just add 4 to your score. I'm not adding 4. Your denominator's not
4
changing.
overall points. Yeah, yeah.
Numerator.
Yeah.
So this was the big proof one, correct?
Yes, and I was just looking over it while you were talking. I kind of remember asking you about this, but I don't still think that I did it. I think it comes down to solving for the constants to show that there are actual constants that will give you a span, I think.
Well, so your work justifies that you can find a C1 and C2. What you're missing is sort of the sequence of the proof. So
Okay.
you went ahead. I'm looking at this now. I got to be careful not to write on it too much because this doesn't work nearly as nicely as my regular surface unit.
Okay.
You started off by making this statement right here.
Okay, yeah.
That's the thing you want to prove.
Okay. So
So your
what?
goal is to so you've got an ODE,
Yeah.
and your goal is to pick an arbitrary solution to it. Now,
Yes.
it says that arbitrary solution can be written as a linear combination of sines and cosines.
Yes.
So what you're going to do is your goal is to show that it can be, but you don't know that yet.
Okay, so when I write that equation, I'm just pulling it from part A, where I kind of solve for it. And then the way I was looking at it is that I have to prove that there are C values that make that true so that I can prove that that will span what I need it to span.
But you don't necessarily know that. So what in the sort of three-dimensional equivalent to this problem, let's say you think that this vector here, let's say you think this vector here, and this vector here form a basis for all of R3.
Okay.
So what are you going to do? To show that it's true, you're going to pick an arbitrary vector and just give it the arbitrary components x, y, and z, and then show that you can write that vector as a linear combination of those three vectors. But you need to show that. So your problem was here when you picked. What I couldn't do is I couldn't say, it would be incorrect to say pick some vector equal to C1 V1 plus C2 V2 plus C3 V3, because then you've already said that it is a linear combination.
So it already is the vector.
Yeah.
Okay.
So
I kind of did circular reasoning then on the test.
exactly. You assumed your conclusion and then said your conclusion was true.
So, okay, if I were to just start that over then, I guess I wouldn't know what, this is my linear combination, right? To the right of that equal sign. How would I
So what I would
that then,
encourage you to do is take a look at the solution that I provided, which might be this one here.
Yeah, I have it pulled up.
And so notice that when I pick this arbitrary solution, I just said, let's let phi solve the ODE. I didn't say phi was a linear combination of my basis vectors.
You just said, suppose phi is that.
Is a solution. And then,
Got it.
well, because of that, if I plug in some time value, I'm going to get out an A. And if I plug in that time value into the derivative, I'm going to get out some B. So my goal is to find C1 and C2 so that we solve the same OD. It's the same.
So that will equal that. Okay.
So in fact, so one way to describe this proof is the whole argument relies on saying, the whole argument relies on saying that we show that our arbitrary solution solves the same IVP as a linear combination of our basis vectors.
Got it. Okay. Yeah.
Since IVPs are unique in this case, those two expressions must be equal to one another.
Okay.
So this is the big conclusion of this first part of showing the span, not the initial statement.
Oh, well, you should. Okay, that makes sense. Okay. Yeah. I think I was just saying this is true. Let me show you that it's true, rather than suppose this were to be true. This is what we need to happen for it to be true.
Yeah. Yeah.
Okay. That makes
I mean,
sense.
and you're on track. And I knew this was definitely by far the most challenging question on this exam. And to a certain degree, it's kind of like the epsilon delta proofs in Calc 1, where you kind of just memorize what.
Yeah. I did the review and I was like, yeah, all the word makes sense, but I think understanding it conceptually is much more valuable, which makes sense.
And
yeah,
so,
cool.
I made the whole thing worth, let's see here. The whole problem was 16 points.
Yeah, I'm actually not worried about the points very much.
Yeah.
I just want to make sure that I knew, like, if moving forward, I needed to understand that in any more depth.
Yeah. And so I think, so here's the thing, Isaac. What we're essentially proving when we do this problem is we are proving that a second order linear ODE solution is a vector that lives inside a vector space of dimension 2. And so, because I don't think it's entirely clear when we say, what's a general solution to a second order ODE, I don't think it's entirely clear that we would be looking for two functions that would be good enough to cover your basis. Literally cover your basis. That would be enough to all solutions can be written as a combination of those two.
Okay, yeah.
And so that to me is actually a fundamental idea in ODEs, in our differential equations class. And so that's why I like to cover this proof. But I also try not to penalize you too much. This part that we've been kind of debating over was worth 7 points for the 16-point problem, just because I don't want to make it a huge, and if you got, if you were on track, you got 2 out of those. So yeah, it was definitely a tough problem, but yeah.
Yeah, I just want to make sure that the concept of what we were trying to show stuck, because I get how to show it, I guess, but I just wanted to understand what I was trying to show.
Yeah, and the key there is that we're just saying, all we know about phi of t is that it solves this ODE.
Yeah.
For all we know, it could be it could be a Taylor series, a function expressed as a Taylor series. It could have logarithms in it. It could have a bunch of radicals in it. Who knows? But we show that, in fact, it can be written as a linear combination of our basis vectors.
Yeah, totally.
Great.
Yep, that makes way more sense. Cool. Thank you very much.
Yeah, other questions, folks? We've got Gelber still here, Evan's still here, Christine's still here.
I was just listening to that explanation.
Good. All right, folks, I'm going to go. I should have done this while